What happens inside a black hole? It's a wonderful question, isn't it? It's the kind of question that makes you realize that everything we think we know about the world, all our common sense, all our daily experiences with dropping keys or watching water flow, simply falls apart when you push nature to its absolute limits. And that is what a black hole is. It is nature pushed to the edge, a place where the rule book gets torn up and we have to start guessing, but guessing with very fancy mathematics and a lot of imagination. Now, to understand what happens inside, we can't just jump right in, because if we do, we get crushed. So we have to sneak up on it slowly, and we have to look at it through two different pairs of glasses. The glasses of Einstein's General Relativity, which is the theory of the big and the heavy, and the glasses of quantum mechanics, which is the theory of the tiny and the jittery, and the problem is these two pairs of glasses don't fit on your nose at the same time, and that's where the real headache begins. We are asking about the ultimate battlefield, where the two great champions of physics, general relativity and quantum mechanics, enter the ring and fight to the death, and we are the spectators trying to guess the winner. To understand the inside, we have to understand how we got there. We have to build the stage, and the stage is space-time itself. Now, you usually think of space as a nothing, a box, a void where you put things, the stage where the actors, the stars, the planets, you and me do our dance. But Einstein came along and said, no, wait a minute, the stage is an actor too. The stage is made of wood or rubber. It bends, it twists, it shakes. And gravity is not a ghost pulling on you. Gravity is the shape of the stage. So when you put the sun in the middle, the stage dips, and the earth rolls around the dip like a coin in a funnel. And that is beautiful. It is elegant. It works perfectly for planets and apples and rockets. But a black hole is not a planet. A black hole is what happens when nature loses its patience. When a massive star runs out of fuel, it stops burning. The heat that was pushing out against gravity dies. And suddenly, crash. The whole thing collapses in on itself. The gravity wins. The matter gets crushed. And the dip in the rubber sheet becomes a bottomless pit, a puncture in the fabric of the cosmos. Now, imagine we are going to explore this, you and I. We're going to take a trip. But we need to be careful, because there is a line in the sand, a circle drawn around the pit, which we call the event horizon. And this is not a physical wall. You can't knock on it. It is a mathematical point of no return. Think of a river flowing toward a waterfall. As you get closer to the edge, the water flows faster and faster. And imagine there is a fish, a very fast fish, that can swim at the speed of light, which is the speed limit of the universe. Nothing goes faster than light, 2c, 300,000 kilometers per second. Now, far upstream, the river is slow. The fish can swim upstream easily, but as you get closer to the drop, the water speeds up, and there is a specific line across the river where the water is flowing exactly at the speed of light. And if the fish crosses that line, even swimming at full power, it will be carried backward. It will go over the edge. And that line is the horizon. So, let's say you jump in, you are the brave explorer, and I stay outside in the spaceship to watch, and this is where relativity plays its best trick, because time is not a steady ticking clock that is the same for everyone. Time is flexible, time is personal. As you fall toward that horizon, the gravity is pulling on the light coming from your flashlight, it is pulling on the information coming from your body, and it is pulling on time itself. To me, watching from safety, you seem to slow down. Your movements become sluggish, like you are swimming through molasses, and the light coming from you gets redder and redder, lower and lower energy, because it is climbing out of a deep gravitational well and getting tired, losing energy, which means its frequency drops. As you reach the very edge, the horizon, to me, you stop, you freeze, you become a permanent image, a ghost plastered on the surface of the black hole, fading slowly to black, never truly entering, just hovering there for eternity, frozen in the last moment of your history. But that is just my truth. And relativity says my truth is valid, but your truth is valid too. And your truth is very different. You don't feel slow. You check your wristwatch. Tick-tock, tick-tock, regular as a heartbeat. You don't feel frozen. You look out the window and you see the universe speeding up, maybe, or looking distorted, but you drift across that horizon without a bump, without a jolt. It is silent. It is deceptively peaceful. But the moment you cross that line, the moment you are inside, the geometry of the world flips. It turns inside out. And this is the hardest part to grasp, but you have to try. In the world outside, you can move left, right, up, down, forward, backward in space, but you must move forward in time. You cannot stop the clock. You cannot go back to yesterday. The future is mandatory. Inside the black hole, space and time swap roles. Literally, the mathematical signs in the equations switch. T becomes R, and R becomes T. The direction toward the center is no longer a direction in space. It becomes a direction in time. It becomes your future. The singularity, that point in the middle, is not a place you are traveling to. It is a moment in time that is going to happen, just like next Friday is going to happen, and you can no more avoid hitting the singularity than you can avoid next Friday. You can fire your rockets, you can struggle, you can try to turn around, but that only effectively moves you sideways in time, or actually might make you hit the singularity faster, because by struggling you add energy and mass to yourself, which attracts you more, so you are falling toward the end of time. And as you fall, you begin to notice the problem with your body, the problem of the tide. You know, tides on Earth, the moon pulls the ocean, but the moon pulls the side of the Earth facing it a little harder than the side facing away, so the water bulges. In a black hole, gravity changes so fast, it gets so strong so quickly, that the pull on your feet is millions of times stronger than the pull on your head, assuming you are falling feet first. This isn't just a gentle tug, this is a violence. It stretches you out, it pulls you into a long thin string, and at the same time it squeezes you from the sides, compressing you, a process we call spaghettification, which sounds like a joke, but is a description of the mechanical destruction of your biology. Your muscles tear, your bones snap, then the molecules themselves are ripped apart, then the atoms are stripped of their electrons, and finally the atomic nuclei are shredded. So by the time you reach the center, you are not you anymore. You are a stream of subatomic particles rushing toward destiny. And then you hit it. The singularity. According to General Relativity, the theory of the big smooth curves, the singularity is a point of zero volume and infinite density, where the curvature of space is infinite and everything goes to infinity. Now, when a physicist sees infinity in an equation, we don't celebrate, we cry, because infinity is not an answer. Infinity means I don't know, it means the theory is broken down, the calculator is smoking. Nature does not like infinites. This is where we need the second pair of glasses. We need quantum mechanics. You see, General Relativity assumes space is smooth, like a sheet that you can zoom in forever and it's still smooth. But quantum mechanics says no, if you zoom in enough, down to the Planck scale, the universe is pixelated, it is jittery, it is a foam. The Heisenberg uncertainty principle, which is the heart of quantum mechanics, says you cannot pin something down to a perfect point, because if you know exactly where it is, you know nothing about its momentum. It vibrates, it fluctuates. So a singularity cannot be a point of zero size. It must be a fuzz, a ball of quantum jitter, a roiling knot of space-time. So what happens there? This is the frontier. Some people think that when the star collapses, it doesn't crunch to a point, but it bounces, like a rubber ball squeezed too tight. But because of the time dilation, the bounce takes billions of years to get out. Or maybe it bounces into a new dimension, creating a baby universe, a white hole in another space-time, expanding out like a big bang. So maybe our universe is just the inside of a black hole in someone else's universe. Wouldn't that be a kick in the pants? But it gets weirder, because we have to talk about Stephen Hawking. He realized that black holes are not truly black because of this quantum fuzziness. In the vacuum of space, empty space isn't empty, it's alive with virtual particles, pairs of matter and antimatter, electrons and positrons, popping into existence, borrowing energy from the vacuum and then snapping back together and vanishing, poof, gone, before you can see them. But if this happens, right on the edge, right on the horizon, the tidal forces can rip them apart. One falls in, one flies away. The one that flies away becomes a real particle, radiation, heat. But the energy for that had to come from somewhere, and it comes from the black hole itself. The particle that falls in has negative energy relative to the outside, so it subtracts mass from the black hole. This means black holes evaporate, they shrink, they glow with Hawking radiation. And this leads us to the biggest headache of all, the information paradox. In quantum mechanics, there is a sacred rule. Information is never destroyed. If I take an encyclopedia and burn it, the information is scrambled in the ash and smoke. But in principle, if I have a supercomputer and I know the laws of physics perfectly, I can reverse the movie and read the book. But if I throw the encyclopedia into a black hole, and then the black hole waits 1 trillion years and evaporates into a bath of random heat radiation, where is the text? Where is the story? Did it disappear? If it disappeared, quantum mechanics is wrong. If it is still there, how did it get out of the prison? This paradox has been driving us crazy for 50 years. Some folks think the information is stored on the surface, on the horizon itself, like a sticker on a suitcase. Imagine a soup can. The soup is the 3D stuff inside, but the label is the 2D stuff on the outside. Maybe the black hole is a hologram, where all the 3D reality inside is just a projection of the 2D information on the surface. And if that's true for a black hole, maybe it's true for the whole universe. Maybe you and I in this room are just a holographic projection from the edge of the cosmos. It sounds like science fiction, but it's the best math we have right now. So deep down inside, what is it? Is it a tunnel? Is it a dead end? Is it a monster that eats information, or a library that stores it? We don't know for sure. We have the pieces of the puzzle. We have the gravity, we have the quantum mechanics, we have the thermodynamics, but they don't fit together yet. We are missing the glue, the theory of quantum gravity. And that is why this is so exciting. If we knew the answer, it would be boring. We could go home and watch television. But because we don't know, because the black hole stands there and defies our logic, it forces us to be clever. It forces us to dream up new ideas, new mathematics, new ways of seeing the world. It tells us that the universe is stranger, deeper, and more wonderful than our common sense can ever imagine. So, inside the black hole, it is a place where space crumbles, time freezes, and the laws of physics are waiting for you to rewrite them. It is the ultimate laboratory, locked behind a door we cannot open, teasing us to find the key. And maybe, just maybe, the key is in thinking about the world not as things, but as relationships, as loops of information, as a great cosmic dance where the dancer and the dance are the same thing. Isn't nature marvelous? So far we have been talking about a very specific, very simple kind of black hole, a Schwarzschild black hole, which is what you get if a star just collapses straight down without moving. But stars don't do that. Stars are alive. They spin, they rotate. Think of the sun, think of the earth. Everything in the universe is twirling like a skater on ice. And when that skater pulls her arms in, what happens? She spins faster, conservation of angular momentum. It's a law you can't break. So when a massive star collapses from 1,000,000 miles wide down to a dot, it spins frantically, it becomes a dervish, and this changes the shape of the beast entirely, giving us what we call a Kerr black hole. And inside a Kerr black hole, the madness goes up to 11. You see, when a mass spins, it doesn't just spin through space. It drags space along with it, like a spoon spinning in a jar of thick honey. The honey near the spoon has to move. It has no choice. And this is called frame dragging, or the Lenz-Thirring effect. And around a spinning black hole, space is being whipped around so fast that even if you had the most powerful rocket engines in the universe and you tried to hover, to stand still relative to the distant stars, you couldn't do it. Space itself is moving faster than light around the center. So you are dragged along. You are forced to rotate with the hole. This region is called the ergosphere. And it's a fascinating place because you can actually steal energy from it. You can dip into the ergosphere, throw a rock into the hole, and bounce yourself out faster than you went in. stealing a bit of the black hole's spin, essentially using the black hole as a giant flywheel battery. But if you fall past the outer horizon and go deeper, you find that the singularity is not a point anymore, because a point cannot spin. A point has no dimension to turn. So the singularity is smeared out by centrifugal force into a ring singularity, a circle of infinite density. And this opens up the wildest possibilities in theoretical physics. If you approach the ring from the side, sure, you get crushed, spaghettified, destroyed, game over. But if you come at it from the top or the bottom, straight down the axis of the spin, the math, and remember, this is just the math talking, we haven't been there, suggests you might be able to fly through the ring without hitting the infinite density. You might pass through the eye of the needle. And where do you go? Do you come out into the center of the star? No, the star is gone. Do you come out in our universe? Maybe not. The solutions to Einstein's equations for a spinning black hole suggest you might emerge into a negative space, or a different universe entirely, or perhaps a different time, because inside the ring, the logic of cause and effect breaks down even more than usual, creating what we call closed time-like curves, which is a fancy way of saying time travel. Imagine a path where you walk forward, step by step, never turning back, and yet you arrive at the moment before you left. You could tap your past self on the shoulder and say, "Don't jump." But then if you didn't jump, you wouldn't be there to warn yourself, and we are back to the grandfather paradox, and nature usually hates paradoxes. So maybe there is a chronology protection conjecture, a rule that says no time machines allowed. Maybe the radiation inside the hole builds up to an infinite blast, just as you try to cross the threshold, burning the time machine before it can work. Slamming the door in your face to keep history safe. But we can't stop there. We have to look deeper at the thermodynamics, because this is where the real beauty lies, the connection between gravity and heat. Remember I mentioned entropy? Entropy is a measure of disorder, or more accurately, a measure of hidden information. The number of ways you can rearrange the insides of a thing without changing the outside appearance. A cup of tea has high entropy because I can move the water molecules around and it still looks like a cup of tea, but a perfect crystal has low entropy. Now, Jacob Bekenstein, a brilliant student, argued with me, well, not with me, but with the community. He said, if I throw a cup of hot tea into a black hole, the entropy of the universe seems to go down because the tea disappears, the disorder disappears. And this violates the second law of thermodynamics, which says disorder must always increase. So he said, the black hole must have entropy, the black hole must be keeping a record of the disorder, and he realized that the amount of entropy is proportional to the surface area of the event horizon, not the volume. And this was shocking. Usually, the amount of stuff you can fit in a box depends on the volume of the box, right? If you make the box twice as wide, twice as deep, twice as high, you have 8 times the volume. But here, the information is written on the area, like the pixels on a screen, and this suggests that the fundamental bits of the universe, the ones and zeros that make up reality, are not little cubes, they are little squares, little patches of area on the boundary of space. This reinforces that holographic principle I mentioned, suggesting that gravity is actually a phenomenon of information processing, that the falling apple is falling because that increases the entropy of the surroundings, that gravity is an entropic force, like the pressure of a gas, arising from the statistical average of billions of little quantum fluctuations. And speaking of fluctuations, we have to talk about the firewall paradox, which is a recent fight in the physics family. You see, we have this idea of monogamy, of entanglement. Sounds like a marriage counseling term, but it means a quantum particle can only be fully entangled with one other partner at a time. Now, Hawking radiation relies on the particle falling in being entangled with the particle flying out. They are a pair linked by fate. But General Relativity says the particle falling in must also be entangled with the space deep inside the black hole to ensure a smooth fall, to ensure nothing special happens at the horizon, which we call the equivalence principle. But the particle cannot be married to both the particle outside and the space inside, that's polygamy, and quantum mechanics forbids it. So something has to give. Either the particle outside isn't entangled, so Hawking is wrong, or the particle inside isn't entangled, so Einstein is wrong. If you break the entanglement with the inside to save the quantum mechanics, you create a shock, a literal wall of energy at the horizon, a firewall. So instead of floating peacefully into the dark, you hit a blazing surface and burn up instantly. This makes the black hole not a hole, but a solid object, a hard shell of quantum fire. Is it true? We hate it. We hate it because it ruins the elegance of Einstein's smooth space, but the math is stubborn and it demands an answer. And while we are guessing about the inside, we are also listening to the outside, because now, for the first time in human history, we are not just looking at the universe, we are hearing it, thanks to LIGO, the Laser Interferometer Gravitational Wave Observatory. When two black holes spiral into each other, they don't just bump, they churn the fabric of reality. They send out ripples, waves of squeezed and stretched space that travel across the universe at the speed of light. These waves pass through the Earth, they pass through you, stretching you by a fraction of the width of a proton. And we built a machine that can measure that stretch. And when we heard that first chirp, that whoop sound in the data, it matched the equations of general relativity perfectly down to the decimal point. It told us that black holes are real, they are out there, they are smashing together, and in that fraction of a second of collision, they release more energy than all the stars in the observable universe combined, yet it is invisible. It is dark. It is pure gravitational fury. But what happens to the stuff inside during a collision? The horizons merge, the areas add up, the entropy jumps, and the new, bigger black hole rings like a bell, a ring down, vibrating until it settles into a new shape. And by listening to that ringing, we might be able to tell if the horizon is a smooth Einstein surface or a fuzzy quantum fuzzball. We might be able to hear the echoes of the event horizon, subtle reflections of gravity that would reveal the quantum nature of the beast. It is like trying to determine the shape of a drum by listening to the beat, and we are just starting to learn the rhythm. We are also looking at the white hole possibility simply because the equations of relativity are time symmetric. They run forward and backward just as well. If you film a black hole eating a star and play it backward, you see a white hole spitting out a star. Does this exist in nature? We haven't seen one, but maybe that's what the Big Bang was, a massive white hole exploding into existence, spewing out time and space and matter. Maybe black holes and white holes are connected by wormholes, Einstein-Rosen bridges, shortcuts through the bulk of space-time. So matter falls in here and erupts there, recycling the universe. It's a lovely thought that the universe is a great recycling machine, wasting nothing, not even the light swallowed by the dark. And let's not forget the string theorists who are trying to tie this all up with tiny vibrating loops of energy. To them, a black hole is a fuzzball, a tangled mess of strings. Imagine a ball of yarn the size of a city. There is no singularity in the middle. The strings just get denser and denser, and the horizon is just the edge of the fuzz. If this is true, the paradoxes disappear because there is no empty space inside. It's all stuff, it's all strings, so the information just sits there in the tangle waiting to leak out. It's a very concrete picture, less mysterious, but very hard to prove. And this brings us back to the philosophy of it all. Why do we care? Why do we spend billions of dollars and millions of brain hours worrying about what happens inside a hole we can never visit? Because it is the ultimate test. It is the edge of our map. The Greeks had the Pillars of Hercules. The sailors had the edge of the world where dragons be. And we have the event horizon. It is where our understanding stops and where the mystery begins. And for a scientist, for anyone with curiosity, the mystery is the fuel. We don't study black holes because they are useful for building toasters or faster cars. We study them because they tell us something profound about the architecture of reality. They tell us that space and time are not fundamental. They are emergent. They are like the heat in a gas, a result of deeper, smaller motions we haven't seen yet. Maybe space is stitched together from quantum entanglement. Maybe here and there are just illusions created by the correlations of particles. It implies that the universe is much more interconnected than we think. that every point is connected to every other point through these hidden quantum threads, and the black hole is where the stitching is pulled tight, showing us the seams. So if you ask me, what happens inside? I have to look you in the eye and say, I don't know. And I say it with a smile, because not knowing is the first step to finding out. If we knew, we would stop looking, but we are looking, we are listening, we are calculating, we are dreaming. We are standing on the edge of the precipice, peering into the dark, and we are seeing not just darkness, but the reflection of our own minds, trying to grasp the infinite. And that, my friends, is the greatest adventure of all. To stand before the impossible and try to understand it. To take the chaos of the cosmos and find the simple, beautiful rules that make it tick. And inside that black hole, in that point of crushed geometry and frozen time, the secret is waiting, the final unification, the theory of everything, hiding in the dark, and we are coming for it.